So this is EE610. We are at lecture 5. So our ultimate aim is to build an amplifier. We first found out what should be the characteristics of a 2-port, 3-terminal nonlinear device such that we can build an amplifier. Then turns out our friends in device physics have already discovered a device that matches well with the large-scale IV characteristic that we wanted. So we picked up one such device, which was an NMOS transistor, and we built our amplifier circuit around it. Right? So how did we connect things on the gate side? So we wanted to bias this gate at some voltage VGS0. How did we do this? So from a battery source VDD, we connected a resistor divider. Such that you had the value VDD into RB by RA plus RB developed as VGS0. How did we connect our small signal source here? So we took our small signal source, some value Vs. A source always comes along with its source resistance, so we have to account for that Rs. And then we connected it through a battery which had the same potential as VGS0, such that you wouldn't have any DC current flowing through this. And whenever you connect this contraption to this point, gate of the MOSFET, you don't change the existing quiescent operating point. Then we said that instead of using a separate battery, I could use a very large capacitor, and then I wouldn't be able to differentiate it between a battery with value VGS0 or a capacitor that is charged to VGS0. So we used a very large capacitor C1 at this node. To bias the drain, I again used the same battery VDD and connected a resistor RL1. And to connect our load resistor RL, I again used a very large capacitor. We called it as C2. Okay. So now this was our gate terminal. This is the drain terminal. This is the source terminal. And you see that in referring to our voltages, we referred the input voltage as well as the output voltage with respect to the source terminal, which was common between the two. Right? So one of the things that we have to do anytime we build a new circuit is to find a name for it. Right? So now we have to name the circuit. Right? And one speciality about this circuit is that the source terminal is common between the input and the output terminal, and it's an amplifier. So can you come up with a decent name for it? So this becomes a common source amplifier. So you got to know the person even before you got to know his or her name. Okay. So this is what we call as a common source amplifier. Now I would like to give you one more perspective on how you could build up a circuit such that you can have two voltages connected at the same point. For example, at the gate node, you now have VGS0 plus a small signal VGS. Right? So to generalize, the problem is this. I have some source VA and another source VB, and I want to connect it using some network such that at the in-between point or at some point in this network, I get alpha times VA plus some beta times VB. Right? So this is what we did when we tried to get VGS0 plus small signal VGS at the gate. We had two sources, one which was derived from VDD, another source which was coming from VS, and we wanted a combination of that to appear at the gate terminal. Right? So I could simply, instead of trying to solve it, in terms of VGS0, VGS, VS, etc., let me simplify the problem a little bit more. Right? This is what I want to do. Okay. Can you quickly tell me how I can achieve this? If I simply wanted alpha times VA plus beta times VB at this node, right? This is now a linear combination of VA and VB. Then what can I do? I can simply add resistors here. Let's say I connected resistor RA here and another resistor RB here. Okay, and I'm calling this as my Vout. Can you quickly give me the expression for Vout? So it will be VA into RB by RA plus RB plus VB into RA by RA plus R. So how are you able to tell this answer so quickly? Superposition, right? You consider one input at the time. So when you consider VA, VB is shorter to ground, right? So then you get this expression very quickly. So your alpha is now RB by RA plus RB and beta is this factor. Can alpha and beta both be equal to 1? Ideally, if we had VA as our VGS 0 and VB as our small signal source VS, we wanted VGS 0 plus VS at the output, right? But if I have a ratio of two resistors like this, right, then I cannot make both alpha and beta equal to 1 at the same time, right? I will have to sacrifice one of the ratios. Now, sometimes this is true. You will get ratios that cannot be weighed to 1, and then you will simply have to bump up the value of VA or value of VB such that you get the required voltage at the output, right? But the particular case we are dealing with is a little special, right? And what is special with our case? Are we dealing with two identical voltage sources? What is same or different about them? So one is large signal, the other is an incremental source. And the other difference is? That is large signal and one is incremental fluctuation around the other. What is the other difference that we say? One is DC and the other is operating with some frequency, right? So our VGS 0 is basically a DC signal, that is the frequency is equal to 0. And our VS source, our source has some frequency, let's say omega equal to omega n. Right? So then instead of just thinking in terms of resistances, we will bring in frequency dependent impedances. Is that clear? So instead of just writing it as RA and RB, let me denote ZA, ZB, and then I have VA, which is DC, and VB, which is at some omega n. Right? Now I still want to calculate the output here. How do I proceed? Same method, but I have to do a steady state sinusoidal analysis or a phasor analysis. And how do we do this? So when you are doing a steady state sinusoidal analysis, you cannot consider all the frequencies at the same time, right? You solve it for the first frequency, then you solve it for the second frequency. So now first let's figure out what would be the output appearing here if I solve it only for DC. What is the answer? So whatever is the VA into ZB, but ZB is a frequency dependent impedance. So I have to specify for which frequency I am evaluating the ZB. So this has to be evaluated for omega equal to 0 divided by ZB plus ZA. What about the contribution from our AC source? It should be 0, right? We are evaluating only for frequency components at DC, right? And the AC source doesn't have a component at omega equal to 0, so that simply becomes 0. Now, if I solve this for omega n, what do I get? Tell me the contribution from VA. 0 plus VB. So whatever is the amplitude of your sinusoid into ZA at omega n divided by ZB at omega n plus ZA at omega n. Is this clear? Okay. So now if I want this to be equal to VA, what comment can you make about ZB and ZA evaluated at DC? So I want this whole factor to be equal to 1. So your ZB evaluated at DC has to be much greater than ZA evaluated at DC. Yes. VB bar, just to show that it is the amplitude of the sinusoid. Because I have just written VB here, you could call VB as, so VB as a function of time and some VB bar into, say, sine of omega n into t. That's it. Okay. Now similarly, I want the component at omega n to be equal to whatever I have given at the input, right? The maximum amplitude. So what is the condition for this? So that would mean that your factor here has to be almost equal to 1. And when do you get that? ZA at omega n has to be much greater than ZB at omega n. So now we have got two conditions. One is that ZB at DC should be much greater than ZA at DC. And then ZA at omega n has to be much greater than ZB at omega n. Right? If I satisfy both these conditions, I would get VA plus VB at the output. Both VA and VB will not be attenuated. Is that clear? Okay. So looking at these two, what inference can you make? So for both of these to be true, either ZB, the impedance of ZB should decrease as your frequency is increasing, right? Or the impedance of ZA should increase as your frequency is increasing, or both, right? So now you are aware of lot of frequency dependent impedances. Can you tell me what are the possibilities that will achieve this? Sorry? So let's say I have ZA and ZB, right? One possibility is the one that we consider, where for ZA we consider a resistor and for ZB we consider a capacitor, right? And the condition that we need to satisfy is both of these. At DC, the condition is automatically satisfied. The impedance of a capacitor is infinite at DC, therefore this condition, first condition is automatically satisfied. What does the second condition give you? Your R has to be much greater than 1 by omega n into C, right? And we also derived it using a different method and got a similar result. We got C should be much greater than 1 by omega n into R. Okay, what is the other possibility? Let's say I use an R for ZB. What can I use for ZA? An inductor, right? Again, once you use an inductor, the first condition is automatically satisfied. At DC, the inductor is going to give you 0 impedance. Now to satisfy the second condition, I simply have to make sure that omega in L, which is the impedance of ZA at omega n, is much greater than R. Now if I can use RC and an RL, I can also use an L and a C, right? Where the condition you will get is simply omega n into L has to be much greater than 1 by omega n into C. So all that this means is you could have a DC bias, you can connect it through a resistor, and you can have an AC signal which you connect it through a capacitor, and provided you choose the capacitor value C appropriately depending on the frequency of the AC signal, you will have both the DC plus the AC signal appearing there with correct magnitudes. Now instead of it being R and C, I could have a L and an R or an L and a C. All of these combinations are going to work out. Now on a chip, we generally prefer to use a capacitor instead of an inductor given a choice, which is why we typically go with this choice. So this is one configuration. The other configuration is inductor followed by a capacitor, or you could have inductor followed by a resistor. Now all of these are called as AC coupling circuits. Right? So coming back to our original circuit, this capacitor C1 and C2, they are typically called as AC coupling capacitors, or sometimes as DC blocking capacitors. Same thing, you're just calling it by two different names. Okay, now a quick question before we move on. Is there a difference between an AC equivalent circuit and an incremental equivalent circuit? Are they same or is there a difference? There is a difference? How many of you think that there is a difference? What is the difference?
Magnitude levels of the sources. So, because we are considering a very incremental circuit, we consider that there is not much change in circuit behavior. But if we consider an AC source of similar magnitude that of DC, we are considering two entirely different half cycles of.
Is that clear to everyone? So, when you say incremental equivalent circuit, the only assumption you are making is that the fluctuations are very small, right? Your fluctuation could also be a DC. When you say an AC equivalent circuit, only assumption is your omega in is not zero, right? It so happens that in our particular case, your small signal source Vs is both incremental as well as an AC source, right? So when we use the term small signal equivalent, it is also with the understanding that the small signal source we are considering is also an AC circuit. But really these two terms need not mean the same thing. Right? Our circuits happen to be both small signal and AC equivalent circuit at the same time. Is that clear? Okay. So now we go back to our calculation of swing limits for the input. Right. Now, so given this circuit, quickly tell me the total gate voltage. VDD into RA, RB divided by RA plus RB plus VS. So if I make the assumption that RA parallel RB is much larger than RS, then I simply have VS here. Okay. What is the total voltage at the drain? VDD minus whatever is the quiescent operating current into RL1 minus GM RL parallel RL1 into VS. Right? So we had started sketching this. So let's assume that this is your total gate voltage. This is around VGS 0. Let's say you have some A sine of omega in t. Okay. So you have a sine wave that looks like this around some VGS 0. And your total drain voltage VD, I'll simply write it as some VD 0 minus GM times RL parallel RL1 into VS. So around a VD 0, how should I sketch it? Inverted sine wave, right? Inverted sine wave, but with a much larger gain. Now let's say I gave a slightly higher sine wave at the input. What happens to the output? I should get a larger sine wave at the output. Do you see a problem? So I have taken an NMOS. I have increased the voltage at the gate, and I see that the voltage at the drain is going to decrease. Right? And if I assume that the gain was 10 times, if GM into RL parallel RL1 was equal to 10, I give 10 millivolt, I would get 100 millivolt swing at the output. So if this was A, this would be 10 times A. Right? So your gate voltage is increasing, your drain voltage is decreasing. Do you see a problem with this, or is it okay? To what region is it going to change? Bilinear? So what is the condition that you have learned for the transistor to be in saturation? Your VDS has to be greater than or equal to VGS minus VTH. Right? So if I look at the ID versus VDS curve, for different VGS, you found out curves like this, right? And the point at which it was shifting from saturation to linear can be traced out using a parabolic curve like this, right? Now let's assume that you initially started with some ID 0 and a VD 0 somewhere here. When I increase my VGS, in which direction am I moving? I am simply moving to the left side. So do I simply go like this? Just like this? I increased the input, right? The gate voltage has increased. VGS has increased, which means I should be moving up. Right? Now along with it, the drain voltage has reduced, which means I should also be moving left. So I have to move up as well as to left. So that seems to suggest that I am moving roughly in this direction. Is that clear? Now would it be a straight line? So we all agree that from some point here, we are moving in this direction. Would it be a straight line, or would it look like this or like this? If I assume that the small signal analysis is still valid, right, then I could say that my ID is equal to GM times the voltage appearing at the gate, right? And the drain voltage VD is equal to minus GM times RL parallel RL1 into Vs. Based on these two, can you comment how ID versus VD would look like? It should be a straight line. With what slope? GM is common in both the expressions, right? Is it minus RL parallel RL1 or minus 1 by? So this is ID versus VDS curve. So if you do dou ID by dou VDS, you shouldn't get a resistive component. You should get a conductance as the, so this would be, the slope will be equal to minus 1 by RL parallel RL1. Okay. So all of this to tell you that whatever is your initial starting point, ID0, VD0, as you increase the gate voltage, you are moving closer and closer to the edge of saturation, right? And what is that exact point? So your total VDS was some VDD minus ID0 into RL1 minus, what is the small signal voltage here? So all that I am trying to do right now is take this equation, VDS greater than VGS minus VTH, and I want to put in the total VDS, total VGS, and see where this relationship is leading us. Okay, so what is the total VDS? VDD minus ID into RL1 minus GM RL1 parallel RL into Vs, right? Now that I am dealing with a sine wave with amplitude A, what do you think is the worst case point for analyzing this? Should I be solving this at this point when the amplitude is 0, at this point at the peak value, right? So I should be looking at this condition for the peak value, because if I have met the condition at this peak value, then I am fine. I don't have to verify at the rest of the points. So instead of writing it as Vs, I'll simply say A, the maximum amplitude of the sine wave. This should be greater than VGS naught, which was VDD into RB by RA plus RB plus A minus VTH. Can you solve this and find out what is the limit on A? So what do you get? A should be lesser than right? So I'm simply going to call this as A max 1. Right? So during the positive cycle of the input, If your amplitude exceeds this value of A max 1, then your transistor is entering into triode region, right? What is so wrong if the transistor enters in triode region? Why is it so bad? What changes?
Gain will change.
How does the gain change?
Transconductance value is
So we already saw that the GM value is going to be much smaller in the triode region than in the saturation region. So that is one part. Your GM is going to reduce, which means your gain is now going to be smaller. What is the other issue? So how did we show this in the small signal model? Y22, right? So you have a GDS which is non-zero, right? A GDS which is non-zero would mean that in your small signal model, you would have GM times VGS flowing through the transistor. Then you will have a Y22, or in other words, which we represented using GDS, followed by the remaining resistance RL parallel RL1, right? Therefore, because I have shown RL instead of writing GDS, I will say RDS, right? So what is the total impedance at the output now? It is RL parallel RL1 parallel RDS. Is this bigger or smaller than earlier? It has become smaller, right? So your gain given by GM times RL1 parallel RL is decreasing because your equivalent load impedance has reduced. Your GM value also has reduced, right? So you can expect to see a drastic drop in the gain. Why is that a problem? The gain drops, so what? Amplifier is not? But it is amplifying for the most part, right? So if I had input, so again around a bias voltage, so let's say VGS0 plus your VS, like this, what do I expect to see at the output? I expect to see an amplified signal, right? Now I give a larger input, should mark out the points where. Right? Now, if I give a larger input, what do I expect to see? Ideally, it should have been a full sine wave like this, right? But at some point here, your transistor is going to enter into triode region. Once it enters the triode region, it wouldn't see the same gain. So what that means is, instead of seeing a full sine wave here, you'd see that it is a little suppressed, right? Now, if I give an even larger input, then beyond a point, it will look like this. So you gave a clean sine wave at the input, you expected to see a clean sine wave at the output, instead you are getting a distorted sine wave, right? So in other words, I had a system. At the input of this, I gave some A sine of omega in t. I would expect to see some amplified, let's say by alpha times, or if you want to use a number, 10 times A into sine of omega into t. Right? Now, once you have a distortion, what is it that you are seeing at the output? You will see multiple frequencies, right? You have a distorted sine wave. If you only had a sine wave and you wanted to analyze the frequency content on it, you would do a Fourier analysis and you will see that only one Fourier coefficient is present and that corresponds to the frequency of omega n, right? Now you have a distorted sine wave. you do a Fourier analysis, you would see that there is a sine omega in t, plus there would be some alpha 1 into sine of twice omega in t, plus alpha 2 into sine of 3 omega in t, etc. Right? So you gave something at omega n, at the output you are seeing omega n plus its harmonics. Right? Therefore, now your amplifier itself has become non-linear. Right? You gave a clean sine wave, you are getting a distorted output. In other terms, you gave something at omega n, you are seeing omega n plus its harmonics. Right? So this process wherein the amplifier is distorting the output from what you really want is simply called as distortion. Right? And we want to prevent distortion. So that means during the positive cycles of the input, there is a maximum value of input beyond which your transistor is going to enter into triode region, resulting in distortion at the output. Okay. So now let's do the same analysis for the negative cycle of the input. What do you think will happen? So during the negative cycle of the input, are you moving closer to triode region or deep into saturation region? If I take this curve, my gate voltage is reducing, right? Which means I have to move down. Gate voltage is reducing, I have to move down. What happens when the gate voltage is reducing? What happens to the drain voltage? Drain voltage is increasing, right? So you have to move to the right side also at the same time, right? So overall, you would be moving along the same line like this. Do you see a problem with this? We might reach cutoff, right? If you extend this line, you get to the point where ID0 equal to 0. Okay. So if this was your input, so we started off by saying that your drain current can become 0. So your total drain current is some ID0 plus a small signal ID. What is the small signal ID given by? That is Gm times whatever is the input you give. So if this was Vs, Gm times Vs. Right? So your ID will also look like this. Right? Where this value is given by Gm times Vs. So now the danger that we are facing is that your total ID given by ID0 plus Gm times Vs can become equal to 0. What happens if the drain current becomes equal to 0? It is cut off, right? What happens to your gain? Gain becomes 0. Why? Because your Gm is proportional to square root of ID. Right? So if ID goes to 0, your Gm also drops to 0. Right? So let's solve for this condition. You have some ID0 plus Gm times, we are now solving for the negative cycle of the input. So if your input is A sine omega in t, during the negative cycle, the maximum negative value it can take is minus A. This should be equal to 0. So what is the limit you get? A should be ID naught by Gm, right? Should it be lesser than or greater than? A has to be lesser than ID naught by Gm. So if you really want your total current through the transistor to be greater than 0, therefore you will get the condition that your A has to be lesser than ID naught by Gm. I could replace Gm with 2ID by VGS minus VTH, and this would give me This is VJ0 minus VTH divided by 2. Okay. So whatever is the quiescent overdrive voltage, half of that is the other limit for your input signal. So this is A max 2. So same as before, if you give a sine wave which is larger than this A max 2, what happens at the output? So you will have a regular amplification around it, but from that point onwards, there is no current, GM has dropped to 0. Therefore, even when your input is reducing further, you don't see a corresponding reduction at the output. It sort of clips off. Right? So there is a possibility that your sine wave can get clipped off at the output during the negative cycle at the output. This happens because the transistor is entering into the triode region. Now during the negative cycle at the input, which is when you get a positive sinusoidal at the output, your transistor could enter into cutoff region and thereby result in more clipping. So now we have gotten two values. There is an A max 1, there is A max 2. If you had to find out an absolute limit for the sine wave, which of these limits would you use? The greater one, the smaller one, A max 1, in between. So if you choose a value that is in between, let's say you chose a value between A max 1 and A max 2, where A max 2 was the smallest one, right? Then during the negative cycle of the input, right, your value is more than A max 2. So you can get a clipping at the output, right? So you don't want to get a clipping either during the negative cycle or during the positive cycle. So whichever between the two, which of them is smaller, you have to make your limit to be smaller than that. Right? So the maximum input you can feed has to be smaller than minimum of A max 1, comma A max 2. So far okay? Now let me ask you a question, right? We said that if our A max 2 was A max 2 has to be smaller than Vj0 minus Vth by 2. If it became greater than this, then the transistor is entering in cutoff. Is that statement right? What is the condition for cutoff? Your total VGS has to be greater than the total VGS should be greater than VTH, right? What is the total VGS? The bias point VGS0. Let's look at the negative cycle. So in this case, it would be minus A, right? Greater than VTH. So I'm assuming that the small signal you are applying is of the form A into sine of omega nt, right? Then the Vs max is simply A, Vs min is minus A. So if I want to calculate the smallest possible potential at VGS, that will be VGS0 minus A. This has to be greater than VTH. This gives you the condition that A has to be lesser than or equal to VGS0 minus VTH. Right? So you're getting two different conditions. Which of them is correct? Where are we going wrong? Take a minute, feel free to discuss and then answer. So let me explain this. Right. If I look at our drain current versus VGS plot, how does the curve look like? So till VT, there is no current. And beyond this, it looks like a parabola. So I'll assume that we are still working only within the saturation region. Right? Now, let's say that this was your original quiescent operating point corresponding to some VGS0 and ID0. Right? In saying that ID0 minus GM times A is going to be 0, all that I have done is I have linearized the property at this operating point and assumed it to be a straight line. Okay? And when I say ID0 minus GM times the input should be equal to 0, I'm looking at the point where the total current has become 0. Okay? And that corresponds to a deviation of VGS0 minus VTH by 2 from your VGS0. Okay, so we have done a linear analysis in finding out this point. Now, if you started off with the nonlinear equations and found out the exact point at which the transistor is entering into cutoff, then you would end up with this point. This is your VTH. Right? So for now, we have called this as our Amax2. But really, if you were to go by theory, this should have been our Amax2, this gap. I shouldn't say that point is Amax2. This VJ0 minus VTH by 2 is our Amax2. Okay. Now the point is this. In saying that, the input signal is large enough that it has hit VJ0 minus VTH by 2 and the gain has dropped considerably, all those statements are correct. The only difference is the transistor did not hit cutoff and the gain has not completely become 0. Right? At this point, if I were to calculate the gain, it would be a different value of gain which is calculated somewhere here, the slope of this line. But that gain itself is so low to begin with. Right? So you have distortion at the output and the distortion is severe enough that operating the amplifier around this point is not feasible. Okay, it's like saying somebody has died in a shootout, but we are questioning whether he died because of 8 bullets or 9 bullets. The person is already dead, right? Our amplifier is already dead. Now there is no point in figuring out whether it's because of VJ0 minus VTH by 2 or it is at VTH. By the time your input amplitude has hit VJ0 minus VTH by 2, your amplifier is equivalent to dead. You cannot operate it there anymore. So we use the tighter constraint of VJ0 minus VTH by 2 for finding out the swing limits. Okay. So now you calculate this, you will find out what your Amax is based on minimum value of Amax1 and Amax2. And in practice, you would make sure you would not operate anywhere close to Amax. You would back off from that point by a large amount. For example, if your Amax is 100 millivolt, you wouldn't cross 30 to 40 millivolts. You will operate it smaller than that. And that ensures a reasonable linear output for the sine wave that you are feeding. Is that okay? So are there any more questions? If you have any confusions, please feel free to ask. So if there are no questions, let me give you a sample problem. Let's say you have a VDD of 12 volt. RS is 0.5 kilo ohm. and this is your Vs. For the transistor M1, VTH is given at 1 volt. Mu and COX is 100 microampere per volt square. W by L is equal to 10. So you can start by first calculating the quiescent operating points. Once you calculate the quiescent operating point, what should be the next major calculation? Small signal. So you want to find out the gain. Then find out. So we spoke about how you have to choose the values of C1 and C2. So determine what C1 and C2 should be. And finally, the swing limits. Okay. Please feel free to discuss with your partner while you are solving this. Huh. For calculating the quiescent operating point, you would de-energize any incremental sources. Because the quiescent operating point is at DC, all the capacitors will be open. And this circuit is sufficient to look at the operating points for the transistor. So what do you get as VGS? This is VDD into, this is at 10 mega ohm, this was at 2 mega ohm. And VDD was equal to 12 volt. So this is 12 into 2 mega ohms divided by 10 plus 2, 12 mega ohms. So this gives you 2 volts, right? Now your VDS0 will be equal to VDD minus ID0 into RL1. Now to calculate this, you need to apply an equation for ID0. And to do that, you need to know the region of operation of the transistor. Is there anything that might hint that the transistor might have a particular region of operation? Nothing, right? So we have to start with an assumption. So we'll assume that M1 is in saturation. Right? Once you assume this, what is your ID0? Then it's given by half mu n COX W by L into VGS0 minus VTH the whole square. So this is half. Mu n COX was given as 100 microampere per volt square. W by L is 10. So you directly get 1000 microampere per volt square into what is VGS0 minus VTH? 1. So this gives you 500 microamperes, or in other words 0.5 milliamperes. Mu n COX is 100, W by L is 10. So mu n COX into W by L together becomes 1000. Right? Now based on this, I can calculate VDS0. That will be equal to 12 volt minus 0.5 milliamperes into RL1. What was RL1? 10K. Right? So how much do you get as VDS0? 7 volt. Now we started with an assumption. So once you get the solution, we have to verify if the assumption is valid. Right? So for saturation region, VDS0 has to be greater than VGS0 minus VTH. right? VDS 0. So in other words, I can directly write it as the drain voltage, the operating point drain voltage has to be greater than operating point gate voltage minus VTH. Is this clear to everyone how I wrote this? Right? So that means your drain voltage can go, how low can your drain voltage go below the gate voltage and still have the transistor in saturation? By one threshold, right? Your drain voltage can go as low as one threshold below the gate voltage and the transistor will still remain in saturation, right? So your drain voltage is now 7 volt. This is 2 minus 1 and this condition is clearly satisfied. So M1 is in saturation. Okay. So next we have to calculate the small signal gain. We will start by sketching the incremental equivalent circuit. Okay, so let's start from the leftmost end. You have your incremental source followed by an RS of 0.5 kilo ohms. Your RB is still connected to ground. So what happened to the capacitor? Incrementally it is still a capacitor, and we have assumed that the capacitance value is large enough that it can be assumed to be a short at the frequency of the input. Right? What happens to RA which was connected to VDD? So the VDD is shorted to ground. Therefore, you will have RB parallel RA appearing here. That is clear to everyone, right? So you had RA from this point connected like this. In the incremental circuit, this gets grounded, which means that is coming in parallel to RB. Okay. Then you have the transistor. Current through this transistor is GM times whatever is the voltage appearing at the gate. Right? And what is the value of GM? What equation would you use here? You can use, actually almost all the values are there, but it will be easier to use 2ID minus VJ0 into VTH. So this is 2 into 0.5 milliamperes divided by how much is VJ0 minus VTH? So this gives you 1 millisiemens. Right? And what is the load resistor? How much is that value? 5 kilo. Okay. So the value of the incremental fluctuation appearing at the gate is Vs into, can you quickly tell me what is RB parallel RA? How much is that? Roughly 1.66 mega ohm. Right? So this is 1.66 mega ohms divided by, let me write this RS in mega ohm. How do I represent this? 0.0005 mega ohm plus 1.66 mega ohm, right? What is a very, very reasonable approximation you can make? Right? You can ignore RS compared to RA parallel RB. Therefore, this is almost equal to Vs. Okay. Now, what is V out? This is your V out. That will be minus GM times Vs into 5 kilo ohm RL parallel RL1. So quickly tell me the gain. This is minus 5 times Vs. So your small signal gain given by V out by Vs is equal to minus 5. Alright, so the next part is for us to calculate the limit on C1. Right? So the corresponding circuit is, you have a Vs, you have Rs, C1 here, and Ra parallel Rb here. Right? And our aim is to make sure that the potential drop Vc appearing around C1 should be as close to 0 as possible, or that the potential drop across Ra parallel Rb should be equal to Vs. Right? And how did we say that we can achieve this? By making sure our C1 was much greater than 1 by omega n times the equivalent resistance that is appearing across C1. How do I find that? So if I call these nodes as A and B, so the circuit that you are looking at right now is completely linear. I can apply Thevenin equivalent. If I do that, you will have a Thevenin voltage, right, with some Thevenin resistance across the terminals A and B, right? And this value of Thevenin resistance is the total resistance that is coming along with the C1, right? And what is that value here? That becomes Rs plus Ra parallel Rb, and we already saw that Rs is much smaller compared to Ra parallel Rb. So please substitute the values and tell me what you get. Your C1 has to be greater than, so omega n is 100 megahertz. So 2 pi into 100 megahertz into Ra parallel Rb was 1.66 megaohms. So what is the limit that you get? Roughly 1 femto. Okay? So this is around 0.95 femtofarads, and you make sure that your C1 is much greater than 1 femtofarad. Any questions here? Okay. So now we do the limits for C2. So you have RL1, C2, RL. Again, we are interested in incremental circuit. So during the small signal fluctuations, we do not want to see any voltage appearing across C2. Right? We want it to be completely zero. Right? The C2 should be completely shorted at omega n. So you'll have RL1 connected to ground, RL here, and some voltage source VJ0 plus Vs. Okay? And again, if you are interested in the incremental circuit, there is no VJ0, it's only Vs. So we repeat the same process. We find out what is the equivalent resistance that is coming across C2. How much is that? What happens to your transistor during the calculation of equivalent resistance? When you are calculating Thevenin resistance, what should you do to the voltage and current sources? You have to de-energize them, right? So if Vs is equal to 0, what is the current, incremental current flowing through the transistor? 0, right? So basically your transistor is also not there in the picture. So now looking at it, can you tell me what is the equivalent resistance that is appearing across C2? So that is RL1 plus RL. Now your C2 has to be much greater than 1 by omega n into RTH. So this corresponds to 2 pi into 100 megahertz into, what is the value of RTH? 20 kilohertz. How much do you get? 79.6 femtofarad. Okay. So this has to be much, much greater than around 80 femtofarad. Okay. And finally, before we start feeding in the input, we need to know how large an input we can feed in. So let's quickly calculate the input swing limits. So during the positive input cycle, the total VGS is going to increase. The total drain voltage is going to decrease. And the total drain current is increasing, decreasing, increase, right? So what is the possibility? This will enter into linear region. Okay. Now, you don't have to by heart the equation that we derived earlier. We start from the basics again. So your VDS0 plus the small signal VDS has to be greater than VGS0 plus the small signal VS minus VTH. What was the VDS0 that you derived? 7 volt, right? So this is 7 volt. What was the VGS0? 2 volt, right? You are assuming a positive input cycle. So I'll directly write it as some A max 1, right? I'm assuming the maximum possible input during the positive cycle minus what is VTH? 1 volt. And what is your small signal VDS? What is the gain that you got? Minus 5. Right? So this will be, should it be minus 5 or plus 5 when I write it here? Minus 5 times A max 1. Right? And this is your relationship between the LHS and RHS. So based on this, can you quickly tell me the value of A max 1? How much do you get? A max 1 should be lesser than 1 volt. Okay. So now we look at the negative input cycle. Right. So during the negative input cycle, your total VGS is decreasing. Your total ID is decreasing. Your total VDS is increasing. So what is the region to which your transistor could change to? Cutoff is a possibility. Okay. And we look at it by checking at what point your total drain current is becoming 0. Or in other words, we want to make sure that your total drain current never becomes 0. Right? So this corresponds to, what was your drain current that you got earlier? So this was 0.5 milliampere. Now here you will have some GM times Vs. So your Vs is some A max 2 has to be greater than 0. Therefore you have the condition A max 2 has to be lesser than 0.5 milliampere divided by, what was your GM value? 1 millisiemens. Right? So this gives you 0.5 volt. So your absolute swing limit has to be the minimum value of A max 1 comma A max 2, and how much is that? 0.5. Right? So now we completely understand how to design a common source amplifier. We know how to choose the values such that it is biased in saturation region. We know how to choose the capacitances. And we also know what are the breaking points for our circuit, how large an input we can give such that your amplifier doesn't work as an amplifier anymore. Right? So obviously this circuit still has some flaws, and we'll learn about those flaws and how to correct it in the next class. Thank you.